Let's go section by section. So permutations, factorials.
Yeah, maybe that one.
That one? Okay. Go back to the appointments. Is holding office hours. So she had 6 appointments, 3 by mail. How many ways are there to order the appointments based on the gender? Clarifier, we're looking for the size of the sample space that lists possible orders like this. Okay. You now have a more structured way of getting to the whole sample space. All right. Okay. Permutation with repetition is needed here. Think carefully of what needs to go in the denominator. Okay. So I think that it's permutation with repetition because I mean, it doesn't matter if male A goes before male B, like it's so that, you know, we're going to take that permutation out because they can be in any order as long as they're male. So that's why you would use permutation with repetition. And yeah, so the denominator, because the formula is n factorial over like number of times an element repeats, I think. Factorial 3 is a number, so the number of ways that you can arrange 3 males, and factorial 3 is a number of ways that you can arrange 3 females, and we're going to use that as a denominator so that we cancel out that from like the n factorial, so that that no longer takes into account the different ways that you can arrange the 3 females in order, because it doesn't really matter which one of the females or which one of the males goes first, second, and third. So that's the denominator. That becomes 36, and then the app total is going to be the numerator, which is going to be just factorial 6, right? Which is just a number of ways in which you can arrange 6 individuals. Divide that by the possible ways to arrange 3 males and 3 females, and then that will give us the app total, which is 20. Yep. And that's basically them fitting the formula in. So you misplaced your iPhone and are afraid that it was stolen. Luckily, your iPhone needs a 4-digit code to get in. Imagine that a potential thief can do 5 attempts at getting the code right before the phone is permanently locked. How big is the chance that they unlock the phone? Think about the sample space and the event space separately. And you'll use. So we're using the probability formula, event space over sample space. So we have to figure out what the event space is and what the sample space is, right? So the total possible outcomes. So the denominator is the sample space, which is all possible outcomes, which in this case would basically just be all possible combinations, 4 item combinations of 10 digits from 0 to 9. And because there's no and it's root replacement, because, you know, you can use a digit more than once. There is, you know, 10 ways you can pick the first digit, multiply that by 10 ways you can pick the second digit, multiply that by 10 for the third, and 10 for the fourth, right? And each time we're picking something between 0 to 9. And every time we pick a number, we still have the same pool of numbers to draw from. So that's why, like, our sample space, i.e. the total possible outcomes that we can have, is going to be 10 raised to the power 4. So there's 10,000 possible combinations. So we all got that, right? So now let's look at the event space, and that's the numerator. And the numerator is 5. And the reason the numerator is 5 is because there's only 5 outcomes, right? Like he has, all right. He can make 5. He can try 5 of those 10,000 combinations and unlock it. That's the event. So like the event space is that, you know, he's able to unlock the phone, and he can do 5 tries before he can try any further outcomes. So if he starts randomly trying 4-digit combinations, he can only do that 5 times, i.e. he can only try 5 4-digit combinations before he can no longer try anything else. So that's why I guess the event space is 5, and I think that's what's in the solution, right? Yep, he's got 5 tries at unlocking the phone.
For 1 second, though, really quick, why did I glaze over the fact? I get that there's 4 digits. Why is it 10 to the 4th? I'm sorry, like all of a sudden it's just.
No worries. So it's 10 to the 4 because we are using the formula for permutations with replacement. And the reason for that is, right, and the reason for that is because it's 10 to the 4 because, all right, so the sample space is, think about it like this. You have a pin on your phone, right? You can set that pin to be 0000. Some people do that. It's not advisable, right? But each
That's
one,
how many digits there are, right? Is what you're getting at.
Right.
There's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's why it's 10.
Yeah. So you think of it like this, where you have 4 slots, right? And each slot is, you can set 1 digit in that slot, right? So let's say when it comes time to set your pin, you have to pick 4 numbers and fill each slot with 1 number, right? But every time you fill a slot, you can pick between 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So you have 10 digits from which you can pick 1 digit to put in that slot. And then when you go to the next slot, you still have 10 digits. So it's not like the pool that you're drawing from is going down with each subsequent selection, right? So that's why it's with replacement. Had it been the case that like you can't repeat any digit, and I think some places like they do that. Remember, like some password sites are like you can't use things in sequence or whatever. But if that was the case, then we would use factorial, because if we pick, like, let's say the digit 1 for our first slot, and we had a requirement saying, well, now you can't use that anymore because you've already used it. So now we have like 9 possible ways left, right? And then when we pick the, let's say 3 for this, then we would have 8 left. So then we would use the formulation, the permutation of a subset, because we're trying to get 4, possible ways to arrange from a pool of 9. But we're not. In this case, because we can use a digit more than once, every slot can be filled from 10 selections. So that's why there's 10 ways to fill the first one. There's 10 ways to fill the second one, 10 ways to fill the third.
You can't see it. Yeah, that's what I was thinking of. Like on Khan Academy, I was like, there's 10, and then there's 10, and then there's 10, and then there's 10. So you just multiply it. Got it.
That's exactly it.
All right. I don't know why, like, it made sense and then it didn't. All right, thanks.
Yeah, that happens. Yeah. All right. So then the probability, now we just have to see, all right, what are the chances that this guy can unlock the phone? He has 5 tries. He can find, like, and at this point, he's just doing it randomly because he has no other way of narrowing down the possible 4 number combinations any further. So he's just going to be trying them randomly, and he has only 5 chances to try. So he can only try 5 combinations, 5 possible permutations. So it's 5 over out of 10,000, and that's the chance that he will win. So the probability that he can unlock it is like, what is it, 0.05% chance. So there's a very low probability that he's going to be able to like hit on the correct code just trying it randomly. So it says, right before you lost your phone, you ate a pretzel and you are pretty sure a grease pattern was left on the 4 crucial digits. The 4 letters in your access code are 3, 4, 7, and 8. And you realize that this information can increase the thief's chance massively. Assuming the thief interprets the smudge marks in an intelligent way, what are the chances that the phone will unlock successfully? So now what's happening here is that your sample space has shrunk. Because before, the guy had to pick, like, there was 10 digits and he had to pick all possible permutations of 10 digits. Now it's shrunk down where he knows which 4 digits they are. He just doesn't know what order they're used in. But he knows that it's only 4, so that shrinks your sample space down dramatically, your denominator down dramatically, which sort of ups the problem. Right, and then the other thing is, now we're switching now from permutations with replacement to just permutations. And the reason for that is because, well, now we know that that 4 digits are being used, right? So when we know that 3, 4, 7, and 8 are the numbers, and we know that it's a 4-digit combination, we know that there's no repetition. So we have a pool of 4 digits, and each time we use one, we know that we can't use that again. So now we're going to switch to using factorials. And that's why it becomes, factorial 4. So what the hell? All right. Yeah. So now we have, right? Hang on. Yeah. So these are our 4 slots. And we know that 3, 4, 7, and 8, those are the only numbers that we can pick from. So in the first slot, we have to pick from 4 numbers. So we have four options of filling up the first one. Now that we've picked one, we only have 3 left, right? Well, it could be in any order, but now for the second one, we only have 3 options. And since we have 2 set up, now we only have 2 options to pick for the third one and only 1 for the last one. So that becomes 4 times 3 times 2 times 1, which is why that becomes factorial. Make sense?
So if one of the numbers were the same, like let's say it was 3, 4, 8, 8, would it just be 3, 2, 1?
I think that's what happens next, right? Like if it was, so the next one is, if we go down, now imagine that you chose an access code containing 3 different numbers with numbers 2, 7, and 8. And the code is still 4 digits. So now the thief knows that one number was reused, right? And that's permutations with repetition. But he doesn't know which one was reused. So there's only 3 possible, there's a pool of 3 letters to draw from, one of which is being repeated. We don't know which one. So to do that, we're going to use, so you'll have to multiply your final permutation with repetition result to account for that, okay? So for the numerator, use the numerator you used before. The number of trials can try before the phone access is blocked, right? So again, the event space is still the same. He can still only try 5 times before it's unlocked, but he has a smaller universe of possible combinations to select from. So it's only the denominator. So the denominator now will become factorial 4 divided by factorial 2. And the reason for that is, can anybody guess why? Because it's a permutation of which formula is it? Let's see.
It's permutation with repetition.
Well, is it?
Because you're using the same digit twice.
You're using the same digit
right?
twice.
You're
right?
repeating it.
Yep, one
so
digit
you have
is
to,
being in. Yep. Yep, so that's the formula that we're using, because we have to find, the possible ways in which to arrange 3 digits where 1 digit is used more than once. So yeah, so it's factorial 4, which is assuming, well, if 1 is repeated, so let's say if 7 is repeated, then we have 4. So we have 4 possible arrangements, but because 2 of these are the same, we're going to take out the possible ways to arrange these 2. So yeah, so we're going to use that formula. So it becomes factorial 4 divided by factorial 2, which is the number of times that the repetition occurs, the number of times that a repeating element repeats. And then we're going to multiply that by 3 because we don't know which one repeats, right? So that means that, if we knew which one was repeating, then what we would do is, we're dividing, factorial 2 divides by the number of possible ways in which to arrange one repeating element, right? But since we don't know which one it is, and there's 3 possible candidates for the element that's repeating, which is why we multiplied by 3, because this part is only going to tell us the possible permutations where we know which element is repeating. But since we don't know, we multiplied by 3 so that, in each one of those 3 iterations, we were saying, all right, well, it's assuming, let's say this one repeats, or this one repeats, or this one repeats. So that's why we multiply the probability or the number of permutations by 3. And that gives us a denominator of 36, is it? Yeah. And then the numerator is still 5. That's still going to be 5.
Because he still gets 5 tries.
Yep, he still only gets 5 tries. Yeah, so that's the part about this that was tricky was, for me, it was really nailing down the concept of event space versus sample space. And what confused me at first was figuring out the numerator. And if you just think about it, we're looking at just what is the universe of outcomes versus what are the outcomes that are valid for what we want. and that was really helpful. Like I really had to go and like read extra material about the concept of event and sample space, and I think that really helped. So like it's a good concept to sort of dwell on, the idea of like event versus sample space. All right, so we got that down. Let's go to the next one. What are the odds of throwing a full house when throwing 5 dice? Recall a full house means that you throw 3 of a certain number along with a pair of a different number. Okay. All right, so let's calculate the sample space. Recall that replacement is possible here. So yeah, any ideas on why the sample space is calculated in that way?
Yes. Does anybody, like, it's 6 sides of a dice times 5 dice. So it's 6 sides raised. That can happen 5 times. Yep. So that's how I interpreted it.
Right. And each dice is sort of independent from each other dice, right? So, you know, you have 6 outcomes possible for the first one, 6 outcomes possible for the second one, 6 for the third, 6 for the fourth, 6 for the fifth. So that's why you just multiply that by 5, because the outcome here doesn't affect the outcome of the second one. So it's not a permutation. All right, so that gives us a sample space of 776. So now let's calculate the event space, right? So the best way to think about the event space here is to split it up into 2 parts. First, try to constrain your problem to a more specific problem. Let's say, how many ways can we throw a full house if we have a pair of 4s and 3 6s? Any thoughts?
Isn't it factorial 3 and factorial 2?
That is the denominator. Well, let's go to their solution and see what they're saying. Let's not look at mine. Yeah, they're saying the same. I think I copy pasted them, probably. Yeah. Yeah, ways to throw a given full house. A pair of 4s and 3 6s. I'm blanking out now.
It's with repetition. So
yeah, that's the formula that we're using, right?
Yeah. Yes,
okay. All right, so factorial 5 would be all possible permutations of each individual digit. And then we're going to divide that by 3. Okay. All right, so we're just going to plug that formula in there. Extend your problem by asking how many different full houses are possible. All right, how many different full houses are possible? How do we know that? Math, factorial 6 over factorial 4. Huh. N over n. So that's permutations of a subset, huh? Okay.
So is that the, so it's how many ways you can throw a 6 and how many ways you can throw a 4?
Is it? Is it? I guess, right?
Because it's just factorial.
Well,
what's the question again? Say it again. Let me see. So the first one is, how many ways can we throw a full house? We have a pair of 4s and 6s, right?
Right, yeah.
And then extend, how many different full houses are possible? So the first one, the event space is how many full houses are possible. That's the event space, right? So at the top is the 4s and the 6s.
No, I think what's happening here is that when they're
throw a full house.
So when they're trying to
oh,
figure,
I get it.
Yeah, because they're
okay, I get it.
Because they're doing it in terms of yeah, ways to throw a full house. I think that that's a different.
So the ways to throw full house is the first line, duh, because that's what it's called. And you take, there's 5 total dice. So there's your factorial 5.
Right.
And the factorial 3 is 3 of a kind and 2 of a kind in your full house. So there's your 3 and 2. because you have to throw 3 of a kind and 2 of a kind for a full
Right.
house. So there's your 3 and 2. And so the different full houses is factorial 6 because that's 6 dice, right?
I think it might be drawing from a different. I think that's a six possible outcomes.
I mean 6 sides? Yeah.
Yeah.
Okay.
So,
And then why is it 4? It's, oh, never mind.
well, good. Well, so they're
I
trying.
was like, it's too different.
They're using the formula for permutations of a subset, right? And we use permutations of a subset to find the number of possible arrangements of k items from n total items, right?
That's right.
So factorial 6 then is the number of unique combinations of 6 outcomes. I don't even know.
Okay, well, I think we build off the 10, right?
Yeah.
And then you take 10, and there are 6. So that's exactly what you're saying. It's a subset. So there's 6 sides to a dice, and the difference between 10 and 6 is 4. Am I off the chain when I think that way? If you're doing a subset? So if there's different ways to throw a full house.
See,
Okay.
I think,
and then this is different full houses.
But I think that there's a kind of a disjoint, because I think that over here they're dealing with 5 dice, and over here they're dealing with 6 outcomes. So I think that
right. So they're going. It's a subset, like you said. It's going on to the 1 dice, the 1 die.
Yeah.
There's 6 sides.
Yeah.
I don't know.
Yeah.
To be honest, anyone
It's
else want to
confusing.
take us down?
Can you close the drawing window so I can read the solution better?
Yeah, thank you, because I have a MacBook Air and the screen is really small.
Factorial 6 divided by factorial 4. Is that what the solution is?
That's part of it. I think that's the second step. They're splitting it up into 2 parts, right? The first part is we're trying to figure out, well, how many ways can we throw a full house, you know, for a given full house. So the idea is, you know, full house of U, 3 of a certain along with a pair of a different number. And they don't have to be in order. So it's not like you have to have, you know, 3 4s together and then 2 6s together. As long as when you roll 5 dice, at the end of the day, it comes out with 3 4s and 2 6s. So okay.
Well, I understand the denominator 3 and 2 because that's the combinations of the full house, either 3 or 2. But
Right.
I don't understand the factorial 5.
Yeah. Yeah, like you would.
I get that.
Yeah.
The different full houses, like probability of k, and k represents how many of something, right? Raised to the n, right? So it's raised to
K,
whatever.
K represents a subset. So if from a possible pool of, let's say, 10 things, you want to select like 4 things, that would be your K. 4 would be your K.
Okay, then it's right there. It's 6 divided by 6 minus 2. So that's what they're doing.
Yeah.
And 6 represents what, though?
The outcomes
How many
of a die.
sides?
Possible outcomes
Yeah.
of a die.
Okay.
Yeah.
And there's 2 different ways to do it, right? There's 2 different ways to get, there's 2 different components. I don't know where the 2 comes from.
There's 2 outcomes, like you have the pair of 4s as one,
Right.
and then the 3 6s is the other.
Got it. Okay. I can get behind that.
Yeah. So n minus k would be 6 minus 4, or 6 minus 2. Right. Right.
Okay, and then that's with replacement. That's permutation. I mean, it's with replacement.
No, that's
That
that's permutations of a subset. That's the formula that they seem to be applying.
Okay.
All right, let's draw it out. I'm sorry, I have a thing for drawings.
I'm very visual too. It's helpful. Thanks.
Yeah. All right, so we have 6 die. Okay, 1, 2, 3, 4. No, we have 5 die, right? Okay. So we have 5 die. Each die has 6 possible outcomes, and we're trying to find the number of ways to throw a full house where you have 3 die having the same outcome here and 3 die and 2 having the same here, right? But they don't have to be in order. So, okay, so let's call it outcome A and B. So outcome A is like the first suit of your full house. So like the example they give is, what is it, 4 or 6 or something? Right, a pair of 4s and 3 6s. So A is 4 and B is 6. And we want 2 4s and 3 6s. But they can occur anywhere. So this could be a 4, this could be a 6, this could be a 6, this could be a 4, and this could be a 6, right? Alternatively, this could be a 4, this could be a 4, the rest of them could be 6s, or the first could be a 6. So let's see, what's the first thing that they do? They find out the ways to throw a given full house, okay? And they say factorial 5 divided by factorial 3 multiplied by factorial 2. Hang on. All right. So why are they doing factorial 5? They're using the permutations with repetitions formula, which is n factorial over each repetition. So factorial 5 is, okay, that's 5 factorial. And that means that they're saying,
there's 5 dice, right?
right, there's 5 dice.
So you're, right.
Mm-hmm.
So that's your
5 times 4 times 3 times
they're kind
2.
of like 5 events
Right.
happening simultaneously.
Right, so they're saying that like, no, wait a second. I think that they're selecting the dice. That's what they're doing. Okay, I see.
They are. So there's 5 dice, and 3 of them have to be the same, and 2 of them have to be the same.
So if you pick, all right, so the 5 factorial is all the possible ways to pick a dice out of 5, right? Or all, so if you pick dice A, then you have 4 dice left, and then 3 left, and then 2 left, and then 1 left, right? But because the order of 3 of them and 2 of them don't matter, that's where the repetition comes in. I see. Okay, so here they're just picking, so the first one is just ways in which to select the slots, right? So just select the actual dice. And, you know.
So that's all the full houses. So it doesn't matter if it's 2s and 3s and 7 and 8s. It's like all of the ways to throw the house. There's 5 dice.
Right.
3 of them have to be one way and 2 of them have to be the other. But it doesn't matter. Like they can repeat, but it doesn't matter what goes where. And then the second one, they're saying it has to be a 4 and has to be a 6.
And that's your denominator, right? Umar?
Yeah. Hang on.
It's ways
right.
to throw, it's you multiply it by that. So it takes out of all the ways to throw it. Oh, you're right. And then it goes into each particular dice, right? So there's 6 ways. So it takes, okay, out of all the ways to throw the, yeah.
Right.
Yeah. So each of the 5 dice, there's 6 sides.
Right.
But they want, fours.
And
Michael, did you say something?
No, I just am slowly getting it. Thank you.
Yeah.
yeah, I think I just got it because on each dice, right, there's 6 ways you can throw it, but you need 2 numbers to be the same. So there's where they get the 2. So on each particular dice, on each individual event, you need 2 to be there's 2 different factors that make it so, to make your event.
I think that the key, so I think the key here is, why are they doing factorial 5 for the first one and 6 for the second, right? And so what that means is here they're just trying to pick the slots, the dice. And, you know, then they're taking out the ways that you can pick 3 and 2 because those permutations don't matter because they can be in any order. So the factorial 5 is all possible orders of dice. So let's label the dice, right? So let's say this is dice A, B, C, D, and E, right? And factorial 5 will tell us all possible orders of those 5 dice. So you can have A, B, C, D, and E. You can have A, C, D, B, and E, and so on, right? But we're thinking about it in a special scenario where we visualize it like, you know, D can occur 3 times, and wait, hang on, let me see. Am I thinking about it right? This is one of those things where you want to kind of, I don't know, at least for me, like I like to sort of
you can draw it. Okay, so draw it. So there's 5 slots when you're picking your dice, right? So after you pick the first dice, there's 4 possibilities. After you pick the second, so there's your 5 slots,
right,
for your first one. So that's how that one goes.
Right.
And then on you're dividing it by the fact that
right.
3,
What are you dividing it? That's what I'm trying to now think about, is how exactly does the repetition come into that model?
Okay, so you need 3 to be the same.
Yeah.
And 2 to be the same. So they can, it doesn't matter really what order, it's with repetition, right? They are in fact on purpose repeating. But there's 3 and 2 to make up that 5.
Right.
On the bottom.
Right.
I think you had it right when you were explaining it, that factorial 5 is all the different combinations that you can have with the dice, and then factorial 3 and factorial 2 are 3 being the same and 2 being the same.
Right. There's 3. So we're dividing it by factorials because we want to remove a set number of possible permutations because they're essentially the same, right? So the way that I think about it is 5 factorial tells us all the possible ways to draw A, B, C, D, E, and F, right? But so let's imagine for a second that A, B, and C are 4, right? Because of that, right, they're not really unique. So we can take that out because it doesn't matter, because then B, A, C, and C, A, B are for our purposes equivalent, because there's still going to be 4, 4, 4, 4. Okay, I think I just got it. Okay. That's what's happening. Okay. So yeah, so that's why first you take all possible ways in which to arrange A, B, C, D, E, and F, right? And then you remove, you know, 2 of these. We don't need F, I guess only E, right? Then we remove from that, you know, the unique combinations of 3 and the unique combinations of 2, and that's why we're using okay, I just got it. All right. Okay, and that will give us the possible ways to throw a given full house, right? Because we're assuming that like the 4 is the 3 and the 6 is the 2 suite. But this could be 3, 3, 3 and 2, 2, 2, or 5, 5, 5, 5, 5 and 1, 1. And that's where the different full houses part comes in, where it's factorial 6 over factorial 4. And here they're using the permutations of a subset formula. Now, why are they doing that? Because here what they're trying to figure out is number of possible arrangements of k items from n total. Okay. So the k is, all right, oh, they're basically trying to pick which 2 should be the ones that constitute the full house individual elements, right? So then 2, all right, I get it now. So there's 6 possible ways to select elements. There's 6 possible elements from which we want to select 2 elements, and those are going to be the ones that constitute our repetitions, so which is why we do, so if we want to select k items from n, we do n over n minus k factorial, or n factorial of n minus k, so that's why this is 6 over 4. All right, so that's, okay, now I get it. So now, so there's 30 different ways to select 2 numbers from 6 numbers, and then there's 10 different ways to get, all right, so that makes sense to me now. I get it. I'm sorry if I dragged you guys through my prolonged and slow thing.
It's important. I think it's important to just talk it. It only helped crystallize it for me.
Yeah.
Yeah, same.
Yeah, I like to kind of slow down and really, like, instead of trying to like power through it, just kind of take a step back and like, all right, what's going on here? I don't know. Like, I feel like when you actually start practicing data science, like I hear that, like, you know, a lot of the stuff is just black box. You just plug it in, and you, like, a lot of people, you don't really have to have like a deep understanding of the statistics behind it, but something about that just makes me nervous.
I know, like I know that math, you can just do math dot factorial.
Yeah.
But maybe I should learn that equation.
Right. Or even like when you get to like the actual, like you could just do like SciPy dot whatever, you know, just do the regression. It'll figure it out for you.
Like,
yeah.
All the stuff that we spend time on in this section, and I'm like, but there's stats models.
Yeah,
like,
for regression.
Do we really need to?
Yeah. Yeah, I guess it's a balance between, like, you don't want to spend too much time because, I don't know, you know, there's so much math to figure out, and you know, is it even feasible to get it all? But on the other hand, I don't want to be like completely going into blind and just plugging stuff into a black box and then getting into trouble because I have no idea what I'm doing.
Or how to explain your result and how you got it.
Yeah.
Exactly. That's my fear as well.
All right. So are we good? And then, all right. So we're good on that. So that's why the event space is now, yeah, like we said, 10 possible ways to arrange a full house, 30 possible candidates to constitute the full house, 10 times 30, 300. That's our event space. All right. So the probability of a full house is event space over sample space, and the sample space is going to be what? It's just going to be like all possible ways to roll the dice, which should be 6 raised to the power. Wait, no, 5 raised to 6, right? No, hang on, am I doing that right? No, 6 raised to 5, right? What is the sample space?
Well, there's how many events? How many events? There's 5 events and 6 possible outcomes for each event.
Right.
So my guess would be 5 raised to the 6.
5 raised to the 6, right?
That's my guess.
Yeah. They never really calculate the sample space anywhere in here, do they? Oh, they do. Yeah, 6 raised to 5. There we go. Okay.
Oh, I went backwards.
Yeah, so it's, yeah.
Okay, wait. Oh, I see. There's 6 sides to the dice.
Right, and 5 dice.
So there's 6 outcomes times 5 events.
Right.
I need to remember that.
Yep. So like,
there's 6 ways it can happen and 5 times that it can happen.
Right. That's
Right?
exactly it. That's
Okay.
exactly, yep. That's all possible outcomes for rolling 5 dice, right? So it's the first dice. There's six possibilities for the first roll, 6 for the second dice, 6 for the third and fourth and fifth, because each dice is independent. It's not really taking anything out from it. We're not doing order. And that's all possible, ways to get those, all possible outcomes of that roll of 5 dice. And then we decided that there's like 300 rolls that meet our criteria of a full house, i.e. where, one number repeats 3 times and the second number repeats twice. And there's 9 numbers that do that we can pick from, to be the third and the 3 repeating and the 2 repeating. And that's where we do all that math. So there's 300 out of the possible 6 to the 5, 7,776. So it's 300 over 7,000. And that's our probability. All right, that was good. I'm glad that we did that.